Hello everyone and welcome back. So today we're going through group problem 2. We're finishing it off. Now this one, oh my, we actually have a real beam this time, everybody. A real beam, not just our cross sections. We're going to have to figure out some math, at least more math. So what are we doing? Well, we have a simply supported composite beam and it's 5 meters long. And it carries a uniformly distributed load W. The beam is constructed of a southern pine timber with a modulusticity of 12 gigapascals, which is 200 millimeters wide by 360 millimeters deep. And it's reinforced on its lower surface by a steel plate that's 150 millimeters wide by 12 millimeters thick. Okay. So with that, what do we want to find? We want to know what the maximum bending stress produced in the timber and the steel if the applied load is 12 kilonewtons per meter. Also, assuming the allowed bending stress of the timber and the steel are 9 megapascals and 165 megapascals, respectively, we want to determine the largest acceptable magnitude for the distributed load W. We're going to neglect the weight in our calculations. Now, I know this seems kind of crazy, but I think you can do this. This is just bringing in how we make our load diagrams from earlier. So go ahead, try out this problem, and if you can't figure it out, don't worry about it too much. Just come on back and we'll do it together. So 3, 2, 1, and you're back. You rocked it. I'm sure you did. And if you didn't, we're going to do it together. So let's try it out. So first off, we're going to transform it. So we're going to say the timber is material 1 and the steel plate is material 2. So with that, our modular ratio is 16.667. It should look fairly familiar. We did a problem earlier with that same exact modular ratio. So we're going to transform the steel plate into an equivalent amount of wood. So it becomes a very big, very wide wood plate. So for our calculation purposes, the 150 by 12 millimeter steel plate is replaced by a wood board that's 2,500 millimeters wide and 12 millimeters thick. Woo! Now let's calculate that moment of inertia. Oh, I have to get the centroid first. What am I thinking? Because it's not symmetric. All these last ones have been symmetric, which has been nice. So first off, we have our transformed steel plate, and we need to figure out where its centroid is. Yes, the transformed centroid as well. We know what its width is, we know what its height is, and so we can calculate the areas. We also know the distance from the bottom to their centroid. So it would be 6 millimeters for the transformed steel plate and 192 millimeters for the wood timber. We multiply everything out, and then we use our nice little equation to say that the centroid will be 137.294 millimeters from the bottom edge of the section. Now, knowing that, we can then calculate our moment of inertia. So this will still be the rectangle, so it'll be 1/12 base height cubed. So the timber has a fairly large one, while the transformed steel plate also still large, but not nearly as large as that timber. The height is cubed, so that timber is fairly tall compared to the steel plate. However, our steel plate is 131.29 millimeters away from the centroid, and it has still an appreciable area. So the correction term right here is 517 million. 517 million. So in the end, they both contribute quite a lot to the moment of inertia. We couldn't neglect either one. So it's 1.5 gigamillimeters. Yeah, 1.5 gigamillimeters to the fourth. Goodness, that's a lot. Now, for our first one, we have a bending moment caused by the distributed load, which is just 12 kilonewtons per meter. So this you can find in your textbook if you want to find out what the maximum is. If you're wondering where we got that, well, you're going to have to do the calculations. You can draw your shear force diagram and see how that works. For now, though, I'm going to let you take that at face value so we can move through this problem a bit quicker. But go ahead and verify that this is true. Verify that this is true. And this is also going to help us out a little bit later. So what we get there is that it's 37.5 times 10 to the 6 Newton millimeters. It would be our max moment for a 12 kilonewton per meter load. Now, what would be the bending stress caused by this? Well, we have our bending moment. We know what the distance is from the centroid to the edge. We want to go to the furthest edge possible. And we over our moment of inertia. And so it would come out to be 5.83 megapascals. And for the steel plate, it would be all the way at the bottom. The reason you don't see anything here is simply because it was 0. The bottom edge is at 0 for that steel plate. And so what we get then is 56.8 megapascals. 56.8 megapascals. I know you don't see an N here. That is a mistake. There should be a N in there for the modular ratio, which is put in there. It just wasn't put in that original equation. Okay, so we've calculated those bending stresses due to a 12 kilonewton per meter distributed load. But now let's figure out what the maximum load we can have is if they can only take 9 megapascals. And we looked previously. Okay, this one can take 9 megapascals, and this one can take 9 megapascals. And you can see that this one would already be way, way over. So it's going to be a lot less this time. Oh, sorry, 9 megapascals was for the timber. Not quite a lot less, but we'll see. So we plug it in here. And we know that our max moment is going to have to be less than this. We know what the moment of inertia is. We know what the stress is. We know what the distance is, at least to the farthest edge. And so the max bending moment for our timber would be 57.925 times 10 to the 6 Newton millimeters. Now, the allowable bending stress for the steel is 165 megapascals. So if we can solve it similarly, then the maximum bending moment is going to be 108.926 Newton millimeters. So 108.926 Newton millimeters for this one, and for the timber it was 57.925. So we can see that the timber would be the one that is controlling this. It's going to be the one that would fail first. So that should be everything. Thank you so very much. If you're wondering why we kept out the negative sign, it's simply because we only cared about the magnitude here. Oh, I almost forgot. And so since this is the highest bending moment, we can then use that in our little max moment equation to solve for the biggest distributed load, which will be 18.54 kilonewtons per meter. Okay, now we're done. That's it. Thank you so very much. I hope you have a wonderful day. Bye-bye.